All right, thanks everybody for coming. We're very excited to have McAllister here to speak today. He's an expert on string theory as it applies to four-dimensional physics broadly and cosmology in particular. Liam was did his PhD at Stanford, moved on to do a postdoc at Princeton, and has since been a professor at Cornell. So he made the short drive up here to give us a seminar today. He'll be here through tonight, so we'll be going to dinner later on this evening. If you'd like to join the dinner, please contact me. And then he's off back to Cornell tomorrow. Today he's going to tell us about some aspects of string cosmology. Thanks very much.
Thanks, Joel, for the introduction, and thanks very much for inviting me. It's great to be back at CITA. I changed the title a little bit to make it more technical, but don't worry, actually, most of the talk will consist of explaining the Axion inflation part, and then by the end I'll explain what exactly we're doing with Calabi-Yau hypersurfaces. This is based on some work that I've been doing over the last several years at Cornell, mostly with my current and former students there. And we have some work coming forward, but most of the key results from today's talk can be found in this paper from earlier 2016. So here's the plan. In the first at least half of the talk, possibly more, I'm going to explain the background behind the use of string theory in B-mode science. What is the role of quantum gravity generally and string theory in particular in cosmological observations? So I'll first refresh you on inflation, describe some key facts about quantum gravity, and then describe the intersection of those two things. What does inflation have to say about quantum gravity and vice versa? So after those generalities, I'll move to a specific construction, a particular kind of model of inflation in string theory involving so-called aligned axions. So I'll describe what I mean by an axion in this context. I'll say what alignment means. And then finally, we'll get to actual enumeration of solutions in string theory. And I hope it won't be until the very end, until enumeration of solutions in string theory, that you really would need any string theory background particularly to follow the talk. So you should definitely feel free to interrupt if I'm not explaining my terms. So let's start with inflation. So inflation, as most of you have heard and some of you know extremely well, is a period of quasi-de Sitter, namely quasi-exponential accelerated expansion in the early universe. The simplest models of inflation involve a potential energy of a scalar field that drives a period of acceleration while the field's vacuum expectation value is gradually moving downward in its potential. And then at some point, the potential steepens, the acceleration ends, and the field moves rapidly, reheating the universe. So that's the rough dynamical picture behind this. And it makes a really striking and beautiful prediction, which is that quantum fluctuations, cartoonishly represented here, in the vacuum state during inflation, are stretched onto the sky. So this tremendous expansion by a factor of e to the 60 in a time period that can be as small as 10 to the minus 33 seconds stretches quantum fluctuations of the inflaton field and also of other fields onto the sky in a form that we see now in the CMB temperature anisotropies, as I'll say briefly in a moment. So the two kinds of modes that were positive are present during inflation are the inflaton itself and the graviton. Quantum fluctuations of the inflaton field get stretched to form primordial density perturbations, which eventually become the CMB temperature anisotropies and form the seeds for large-scale structure. And at the same time, quantum fluctuations of the gravitational field are also stretched, and these form primordial gravitational waves. These we could hope to detect through the imprint that they leave in the polarization of the CMB. So inflation made the following predictions, well in advance of any meaningful measurements of these quantities, except for this first one about the background universe. So inflation was cooked up to solve a problem of the universe on large scales. And it achieves that. It predicts that the universe on large scales should be nearly homogeneous, isotropic, and flat. But the theory then made additional predictions, which is a spectrum of scalar perturbations that are nearly Gaussian, characterized only by their two-point function, adiabatic, with just one fluid fluctuating, scale invariant, or nearly scale invariant, not precisely so. And then this last one, by far the most striking and the most potent evidence for inflation. Inflation predicts that the scalar perturbations should have phase correlations on superhorizon distances. So that means that on distances larger than the width of a light cone at the appropriate time, all of the modes are, for example, cosines rather than some cosines and some sines and others in between. Everything is synchronized. All the perturbations are synchronized. That's what I mean by phase correlated. And there's no causal physics that can set up that kind of correlation. Now, the consequence of these phase correlations is a spectrum of acoustic peaks, which I'll picture momentarily, and an anti-correlation between the temperature perturbations and a particular mode of the polarization, both of which I'll show you. Inflation makes an additional prediction, which is that the primordial gravitational waves, which remember are fluctuating also, the graviton's fluctuating also, should in principle be visible at some level, although there's no prediction that the amplitude should actually be detectable by constructible instruments. So the theory makes a definite prediction that there are primordial gravitational wave perturbations, but it does not warrant that we ought to be able to detect them ourselves. So if we take this beautiful picture that Planck has given us of the CMB temperature anisotropies and represent it in terms of spherical harmonics, then you see the spectrum of acoustic peaks that was claimed. So here's small angular scales, large angular scales. And by staring at this, you can see evidence for many, although not all, of the predictions I claimed. So I'm happy to discuss this afterward. I know many of you here have sat through or contributed to talks on inflation and the CMB, so I don't want to spend a long time developing this subject. But if you haven't seen it before, just take it from me for now that these predictions are easily obtained, are easily found to be manifest in what Planck is seeing in the temperature anisotropies. Now that's not all the predictions so far. To get the remaining ones, we have to look to polarization. So here's the picture Planck has given us of the polarization of the CMB. This is a cartoon of how we might try to decompose this vector field. So think of this as a vector field on the sky, and you can decompose it into a gradient component, which is curl-free, and a curl component, a so-called E mode and B mode. And this is just such a nice picture, you have to zoom in and stare at it for a while. So it looks really nice. So you can picture yourself trying to pull out the E modes and B modes. And suppose you do. Suppose you pull out the E mode component, the curl-free component, and plot the correlation between the temperature and the E mode. Same coordinates as before. Then here, this bump occurs on angular scales that are larger than the size of the horizon at the time that inflation ended. In fact, at the time that these modes exited. And so there's just no way that any causal physics could set up that particular bump. You would expect to see something around 0, no meaningful correlation, in the absence of super-horizon phase correlations. And so this, I think, is the golden evidence that inflation, or something very, very similar to inflation, actually did happen. So right here, we could stop if we were trying to keep track of the successes of inflation. We could say, you can reproduce all cosmological observations with just the 6 parameters of lambda CDM. So a universe with matter, dark matter, and a cosmological constant, plus initial conditions, super-horizon phase correlations that we see evidence for here. That doesn't mean you solve all the problems of the early universe. In particular, in this framework, there's no answer to the question what came before inflation, how did it start, and what is the inflaton field and what dictates its properties. And for all of us who are thinking about the very early universe, some of these questions should keep us up at night, because we really don't know how and why it started the way it did. For me, this is the one that keeps me up at night. What is the inflaton field and what dictates its properties? Not because it's necessarily any more important than this other more initial question, but because this is a problem on which we're actually getting traction in string theory. We're developing some means of understanding what the inflaton field might be and how to compute its properties. So you can sort of feel that this could be achievable. Now on to B modes. So far we've talked about temperature and the E mode polarization. There's one thing left, the vorticity component, the B mode component of polarization. So most of us were electrified when the BICEP 2 collaboration announced that they had detected B modes in the cosmic microwave background on degree angular scales. The detection was correct. There are B modes in the CMB on degree angular scales, but unfortunately, it appears that what they were looking at was polarized emission from dust in the Milky Way, now pictured here as given by Planck. And if you zoom in on the region, this is the region that BICEP was looking at, and pictorially at least, it's clear that there is significant contamination from the polarization, and extremely careful analyses bear this out. So the summary of the status of B modes is not yet detected. But remember, the theory doesn't promise that they should be at a detectably large level. And most of this talk will be attempting to understand what does fundamental theory tell us about whether we should or should not expect to see B modes. If we look a little harder, right? If you look a little harder, you can try and peel away these foregrounds and see if there's a signal underneath. But a task for more fundamental theory is to explain what's the expected amplitude of the signal. Lots of people are looking. It's a really impressive collection of efforts around the world and by many different means. And the question I'd like to ask, as a theorist attempting to be useful in this subject is, can we give even one model that would be ruled out by these searches if they met their design qualifications? I don't mean one model where if they were lucky and there's a especially nice signal out there. I mean, if they perform up to specifications, will they have ruled out anything that a strong majority of theorists would judge to be plausibly consistent? Not will swear is consistent, we'll just judge to be plausibly consistent. Or at least, let's say, one that demonstrably satisfies all known or all credible quantum gravity consistency conditions. So I haven't told you a word about quantum gravity consistency conditions, and this talk is partially about that. But I just want to lay out the theme at the beginning. We're trying to understand, is there anything out there that they should be looking for or not? I should say, I do think that there exist such models. I feel pretty strongly that they exist. But I can't give evidence for them that I believe you ought to accept. So, if you work on it yourself, you might convince yourself one way or another. But I can't tell you, really, I can't browbeat you and say you better accept my argument. And nor can I persuade a lot of the string theory community that these models actually exist. So, if you look in the Planck analysis, you see what looks like a zoo of models. So I'll describe what the axes are, but it doesn't much matter. Okay, so the axis here is the tensor to scalar ratio, the amplitude of the primordial gravitational wave signal referenced to the amplitude of the temperature anisotropies. And this is the deviation from scale invariance. The only thing that really matters is there are a bunch of different models here. Some of them are arcs, some of them are individual points. Doesn't much matter. And here's the theorist's conception of what things might look like 5 to 10 years from now. That could be the allowed region if people do pretty well. So just between this and that. So it looks like, wow, there's all this realm of the NSR plane that's going to be completely ruled out if these experiments go well. Yes, but we should ask, what is the theory population of the region that's being excluded? Okay. So is there even one model in that region?
Do you expect a shift?
The shift?
Shift on NS.
Expect what?
You expect a shift? Is that what you're saying? Like NS?
I don't have a strong expectation, but I sort of like 975 personally. Yeah. No, I had to guess, right? I mean, yeah. Okay, so what is this issue with consistency? What do I mean by does there exist even one? And there are tons. There are tons of papers. There are thousands of papers describing the characteristics of models of that form. So what do I mean, are there not any? Well, in quantum gravity, a useful notion has been landscape versus swampland. So by landscape, we mean theories that are possible in quantum gravity. And by swampland, we mean theories that are not. So what does possible in quantum gravity means? It means you have a quantum field theory, a flat space theory, and you try and attach that to dynamical gravity, general relativity, and treat it as a quantum theory and go all the way to high energies. At some sufficiently high energies, you are studying, for example, graviton-graviton scattering. You want to know whether that continues to be well-behaved as a theory. Not nice, but just acceptable. So when I say that these things are impossible, when we say something is in the swampland, we mean it has a manifest failure of well-behavedness. For example, it might fail to be causal. It might have closed time-like curves of bad types. Or it might fail to be unitary, meaning that the probabilities don't all add up to 1 at the end of some process, although they did at the beginning. So these are catastrophic failures of predictivity in a theory. And so I'd like to know, are there any theories in the landscape that have a large primordial gravitational wave signal, and so could be seen by the coming generation of experiments or ruled out? Now, you could well ask, well, it's nice for quantum gravity theorists to have some ivory tower undertaking of trying to differentiate all the theories in the world into nice and not nice theories. But what does that have, why do I have to apply that to inflation. You know, you wouldn't let me do this kind of thing for modifications of the standard model, probably. So why does inflation actually depend on quantum gravity? So I should say a couple words about quantum gravity itself. It starts with just dimensional analysis. So the Planck energy is a very large energy. In particle physics units, it's 10 to the 19 GeV. And it's obtained by just taking h bar c and g Newton and forming a quantity with dimensions of energy. But it's an extremely large energy in terrestrial terms. So if you take one Planck energy, that's about 8 Teslas. So you can fully charge 8 Teslas with one Planck energy, and you'll pay $100 for that much electricity. And that goes into 10 to the 30 particles, up, down, and electron. Now, if you take all of that energy and you put it in one fundamental particle, then you're in the Planckian regime. Okay, so that's what it means to be near the Planck scale. So if you do that to one particle, then the Compton wavelength of the particle, say it's an electron, the Compton wavelength and the Schwarzschild radius become comparable. So then the characteristic scale of quantum indeterminacy and of general relativistic determinacy, namely whether you're inside or outside a black hole, become comparable. And so something has to give. You can't have quantum mechanics and GR both the way that they naturally exist. Now, if you try to just forge ahead and you treat quantum gravity as a field theory, and you say, well, I know how to deal with field theories. I do computations with Feynman diagrams. So here's a cartoon of neutron scattering by graviton exchange. How do you do it? Well, you find a dimensionless expansion parameter, and graphs with more gravitons being exchanged carry more factors of that small parameter, hopefully small parameter. And then you can compute in perturbation theory. But the problem is that the coupling here is coming from the Newton constant, which in natural units has dimensions of length squared. And so to make something dimensionful, it turns out you have to put in 2 energies. So you can put energy squared in the process over Planck energy squared. So now if you're studying energies, scattering energies that are very small compared to Planckian energies, which is essentially every scattering process that humans could ever construct, then these corrections are negligible. But if just theoretically you were to extrapolate to energies that are larger than Planckian, then this expansion makes no sense whatsoever. So we say this state of affairs, we summarize it by saying that the theory is not renormalizable. You would have to adjust an infinite number of parameters to make sense of it. Now that in itself is not the end of the story. This does not completely ruin quantum field theory. If you have a non-renormalizable quantum field theory, then Ken Wilson explained to us how to deal with that, how to think about it. People had previously learned how to deal with it. The infinities show up at some characteristic energy scale. We call it the cutoff scale. And in gravity, it's the Planck energy. So how do you deal with a theory like this? If you're performing experiments at energies that are small compared to the cutoff, then the high energy physics decouples. It makes small corrections that are suppressed in powers of E over lambda. You can then use an effective field theory that encodes these effects. In fact, in astrophysical gravity, you don't even need to include any of the corrections. The pure classical theory suffices. So that's nice, and this is something that we're quite familiar with in particle physics. Like in the standard model, you know how beta decay occurs. There's a W boson that comes along and then decays. But before W's were understood, Fermi wrote down this interaction. An effective interaction of 4 fermions. He just wrote down 4 fermions in the Lagrangian with a dimensionful coefficient out front. And Fermi's constant is directly related to the mass squared of the W bosons, not then discovered. The relationship between these two theories is if you take the theory that has all the high energy dynamics of W bosons, and you work at lower energies, you don't see W's propagating anymore. You don't make W's. You just see the traces behind of the interaction that they induced. Okay, now this is an important picture for us to have in mind. This is the way we can think about integrating out and partially decoupling high-scale phenomena. Now this works. So separation of energy scales controls our ability to do science. Right? If you want to understand waves on water, you don't need to know anything about quarks. You in particular can't imagine that by performing precise experiments in hydrodynamics, you can learn the relative mass of the charm and strange quarks. It just doesn't make any sense. The energies are totally incommensurate. The energies per quantum. So you might be saying then, well, why don't I just then decouple quantum gravity and forget about it, and we'll just do low energy reasoning and not think about ultraviolet scale physics. There are some circumstances in which you can't decouple high-scale stuff. Extreme circumstances. So in the singularities in black holes, maybe black hole horizons, and especially for us, inflation, cosmological inflation. So the draw of cosmology, particularly, to a quantum gravity theorist is it provides an extremely rare arena where the results of our computations are essential to interpreting the dynamics. This cosmology is an arena, early universe cosmology at least, is an arena where quantum gravity does not decouple, as I will explain in this talk. Okay. So now here comes the claim. I'm not going to prove this claim to you, although I'm happy to give supporting evidence of whatever sort you like. I'll first state the claim, and then I'll give you a picture of what the claim means, and then we'll follow up on it. So claim, an order 1 change in the spectrum at the Planck scale ends inflation. If this is true, if changing the spectrum at the Planck scale by a modest amount changes whether inflation even happens, changing it by an even more modest amount could affect what inflation predicts in detail. In particular, you can adjust the spectrum at the Planck scale and change whether inflation predicts a large homogeneous universe or not. So you can completely ruin inflation by adjusting the spectrum at the Planck scale. What does this look like? Here's a cartoon. Vertical axis is energy. The green blobs down here are, let's say, the mass of some inflaton field. And then as the energy gets higher and higher, closer to the Planck scale, which is here, we see excitations of, let's say, a string, more and more excited strings, and then black holes, bigger and bigger black holes. And if you compare these 3 columns, they're all the same below the Planckian energy. But above the Planckian energy, well, this one has some string on the black hole. And that's a real thing. We have solutions like that. And here, the black holes, these 2 black holes are a little bit closer together in mass than in these other 2 columns. This is what I mean, this versus this versus this, by an order 1 change in the spectrum at the Planck scale. Okay, you just change where the different states sit by a little bit. And here's the amazing thing. If this theory gives rise to 60 e-folds of inflation consistent with all observations, then these 2 theories will end in a big crunch after a roughly Planckian time. So those kinds of changes make night and day differences in terms of whether inflation can happen at all. And this here is the core answer to the question, why is quantum gravity relevant for inflation? The answer is the spectrum of states at the Planck scale doesn't decouple from the inflationary dynamics. Now, this may sound like something that shouldn't have happened. If you want to convince yourself, one story you could start to tell is, well, we know that inflation involves really strong gravitational fields for the accelerated expansion, and strong quantum effects, fluctuations of the background. And somehow you might imagine that those strong quantum effects and strong gravitational effects can interact. I would not be convinced by that argument, but detailed calculations, which I can show you afterward, bear this out. So this is a statement that we're very convinced of because we've tried it many, many times and proved it in quite a bit of generality in string theory, a theory of quantum gravity. So that's the main finding. So what are we supposed to do about this? We should understand why exactly the potential, so what is it that's causing these failures so we can figure out how to solve the problem. So another way of explaining where the problem originates is the following. Suppose you insisted on being agnostic about quantum gravity. You said, I'm going to work at very low energies and I'm just going to compute the scalar potential V of phi, we'll call it V0 of phi, and I'm going to use that and I'm going to study the Friedmann equation, solve, find what the evolution is, and not worry about all of this string theory business. What you would find, if you then went to a friend who was not agnostic about string theory, is that the term you compute would be the first term in a Taylor expansion in phi over m Planck, phi the inflaton field Vev. And the coefficients in that expansion are functions, some reasonable functions, of the mass spectrum of the Planck scale theory. So if you mess with the masses of the various states, you move from one left to middle to right tower in my previous slide, you change the arguments of this function C, and so you change the Taylor coefficients. But if you have a Taylor expansion in phi over m Planck, and you start changing the Taylor coefficients, then your potential is going to change dramatically. It'll wiggle around. And the characteristic scale over which it does that is m Planck. So the summary then is that the inflaton potential generally has structure on scales of order m Planck. It's not smooth, monotonic, with a good monomial description over distances larger than m Planck. What I've explained to you now is a universal phenomenon. You could call it the ordinary universal dependence of inflation on quantum gravity. This I've described so far. In fact, though, there's a special subclass of models where this effect is even stronger. Okay. And that's what I'll be focusing on for the remainder of the talk. But I don't want you to go away thinking that the dependence of inflation on quantum gravity is restricted to these special models. It's not. But in these special models that I'll be talking about, it's even more of an exciting effect. The special models are precisely those models in which the primordial gravitational wave signal is large enough that you could envision seeing it. So in precisely those models where you could imagine detecting primordial gravitational waves, you have to confront the problem of this Taylor expansion in phi over m Planck. So here's the core result in this relationship. David Leith in 1996 established this relationship. The inflaton displacement in Planck mass units is at least as large as the tensor to scalar ratio in units of 10 to the minus 2 to the 1/2 power. And despite many, many attempts to circumvent this, there are no powerful, meaningful parametric ways around this relationship. So that means that, I should tell you, the current limits are around 0.1 now. And you could imagine getting into 0.01 in the next 5 years, perhaps. Those of you who are experts in this, I'm happy to hear afterward what your best guesses are for how well we'll do. But roughly 10 to the minus 2 is a good expectation for mid-2020s. So if we see this in the coming decades, then we'll know that the inflaton displacement is larger than m Planck. Which means that instead of looking rugged on Planckian distances, which is what the theory predicts, we will know from experiment that the potential is very smooth. And that's a really striking thing. That means that we will have falsified the generic expectation, and we will have found that somehow experiment could be then telling us that something very special is happening. So here's our task for the remainder. If we want to know whether there are any consistent theories in this plot that are in the region that could be ruled out by detecting by excluding primordial B modes, what we have to figure out is, can scalar potentials arising in well-behaved quantum gravity theories actually be smooth over super Planckian distances rather than having features and structure on Planckian distances? Okay, so this is the end of the first part of the talk. Now would be a great time to ask questions if you have any questions. Yes, please.
Is it not possible to power the inflation with physics or just Jones standard all but not quantum gravity somehow? That you would not get this kind of company?
Yeah, very good. Yeah, so, right, thank you. I should have made quite plain when I talked about this universal dependence. One's natural thought when you hear that something doesn't quite decouple is to think, and this is true for all other phenomena except this one, all other decoupling phenomena except this one, is to think, oh yeah, that didn't quite decouple because the energies being probed were pretty close to the energies of the underlying physics. You know, you just study flavor physics at 1,000 TeV, at TeV, 10 TeV colliders, it's sort of just around the corner. That's not the reason here. It's not just that inflation occurs at high scales and so it's a little bit sensitive to quantum gravity. It doesn't matter whether this has no relationship whatsoever to the standard model. Even inflation, even if we didn't worry about reheating the universe and baryogenesis, and I tried to inflate at 10 to the minus 100 electron volts, I would still need to worry about quantum gravity, 10 to the 18 GeV corrections, actually. It's a striking consequence of, roughly speaking, the fact that the inflationary eta parameter, which is one measure of these kinds of corrections, is v double prime over v m Planck squared. And whatever scale you put in v cancels out in this computation. This is a figure of merit for quantum gravity corrections. It's a thing that affects the number of e-folds of inflation, and it roughly cancels. Is that getting at your question? So no, this doesn't have to do with limiting assumptions we've made about some simple extensions of the standard model. It would require that we totally rethink everything about quantum field theory. which is possible. Any others? Okay, so how do we go about this task? We want to know whether the field space looks like this or like that. Is there some symmetry that somehow structures it? So this is the natural scale in this problem, like the width of these columns. But somehow it gets structured over much longer distances. Can that happen? That's what we'd like to know. Now, we're going to go about this in string theory, because string theory is our only really workable quantum gravity theory, where we can easily connect to quantum field theory computations. And I'm going to focus on one special candidate, an axion field. I put axion in quotes because this is not the QCD axion, particularly. It's like it, but and like the QCD axion, it's a pseudo-scalar field, so it's odd under parity. And like the QCD axion, it's a pseudo-Nambu-Goldstone boson. Namely, it's associated with a broken global symmetry. But that's where the similarity ends. It doesn't have a theta F dual coupling to QCD. Why am I thinking about this particular field? Well, I don't want to gradually dispatch all the alternative theories, but after some struggling, we've zeroed in on axions as probably the most promising candidates for answering this question: is there anything in the NSR plane that could be ruled out by coming searches before the searches are complete? In other words, there are lots of other theories where I could try and solve this problem over longer timescales, and I wouldn't bet on solving that problem, on figuring out whether there exist models in the detectable range in less than about 5 years. Here, I think we might be able to do it, so we're trying. That's the reason we're focused on axions. What's nice about axions is they're protected by symmetries. So the potential, here's the Lagrangian for a single axion field phi. Okay, so an axion enjoys an all orders shift symmetry, like Goldstone bosons do. Phi goes to phi plus constant. That's broken by instantons to a discrete shift symmetry. Phi goes to phi plus 2 pi f. F is a quantity with dimensions of mass, which is known as the axion decay constant. So this, for the purposes of this talk, we'll be taking this as a given that axion Lagrangians take this form, and we'll be trying to figure out what is the consequence of this kind of form. There are no terms like m squared phi squared. Those would be inconsistent with the shift symmetry phi goes to phi plus constant. So that's where all the niceness of axions comes in. Now, if you look at this theory, the potential is a cosine. And so the fundamental domain of the periodic identification phi goes to phi plus 2 pi f is the region between two adjacent bumps of the cosine. And that region has width 2 pi f. If you were inflating in a potential like this, you're not going to go over the bumps because of energy conservation. So you'll make it from one bump to another bump. So the effective diameter of the field space for the purposes of this theory is 2 pi f. So what we want to know is, can we have f, or 2 pi f, bigger than or much bigger than the Planck mass? If we can, then you can get a model with large primordial gravitational waves, and you've got a target for your searches. And if you can't, then we still come up empty in attempting to populate the experimental target region. Okay, so now I'm going to give a slide of collected lore. The following slide may be rather confusing, and I'll just give an overall summary of it at the end. It may be rather confusing because I'm attempting to describe a whole bunch of things that people have been thinking for the last 15 years, but no one has been able to sharpen into a theorem. So it's folklore. The folklore is that it's hard to compute in a region where f is larger than m Planck. It's also the case that we can usually find in quantum gravity theories instantons whose action is proportional to m Planck over f. What's so bad about that? Well, if f is large compared to m Planck, then s instanton is then a small number. When you have instantons with small action, e to the minus s is order 1, not small. And so the semi-classical expansion, in which you can usually neglect non-perturbative phenomena, breaks down. That means, if instantons like this exist, you can't ignore quantum gravity non-perturbative effects, which is a really bad situation to be in if you want to do computations. And finally, there's just a conjecture that says many other things, but in particular implies that this should not be possible. I'm not going to go through these things individually in any more detail, because all I want you to take away from it is that no one has yet succeeded in giving an example with f bigger than m Planck. So we have to approach the problem in some sort of sideways way. We won't go at this head on. We'll try and come up with a way around the problem. It turns out that all three of these constraints are far less constraining in models of more than one axion than they are in single axion theories. So now here ensues about 6 slides of planar geometry and linear algebra. This is our sort of core calculation. But all of the physics has been stuck behind us in the motivation for this computation. So right now we're going to be studying Lagrangians of multiple axions. I'll assert what the form of the Lagrangian is in a natural generalization of the single axion Lagrangian that I described to you. And all we're interested in doing now is computing the diameter of the fundamental domain, analogous to this diameter in the single field case. Okay, that's our present task. And I'll take you through this calculation because you'll see roughly where it is that the trick has to happen. And that trick is the thing we're hunting after. So here's a Lagrangian of Einstein gravity coupled to n, some number n, of axion fields, theta, with a kinetic matrix K and some potential. This kinetic matrix is just a constant symmetric matrix. Doesn't depend on the fields. And what's this? A sum of cosine potentials. And in each cosine potential, there's some matrix of coefficients QAI, which you can think of as integers. This is just a matrix of integers. This could be like cosine theta 1 plus cosine theta 1 plus 3 theta 2 plus et cetera. Okay, just integer linear combinations of the underlying fields. So what does this Lagrangian tell us? Well, we want to know how big is the field space. Because if we know how big the field space is, we know how big the primordial gravitational wave signal can be. And I've asserted to you, I didn't demonstrate to you, but I've asserted to you that, in my opinion, this is the cleanest corner of quantum gravity for asking that question. The way you can see that it is a comparatively clean corner is I have managed to reduce the problem to linear algebra and planar geometry, and usually we're dealing with much hairier things than that. So what's the diameter of the field space based on this? Well, each individual cosine term sets up a pair of hyperplanes. You can view the points at plus and minus pi as hyperplanes in the line. Now in the general n-dimensional space, Rn, where the thetas live, each cosine gives you 2 hyperplanes, the one here and the one there. So for example, this and that, or this and that. And what we're interested in is studying the region bounded by those pairs, the region that sits inside all such pairs. That's what, well, it's a polygon in the plane. More generally, it's just known as a polytope. So it's an n-dimensional generalization of a polygon. And so we're interested in studying polytopes in Rn and asking how big are they. Now, not how big are they in the trivial metric on Rn, but how big are they in this metric, the physical field space metric, the one that's given to us by the underlying theory. Okay, so all we need to do is compute that diameter. So how do we do it? By change of variables. Okay, so here is the Lagrangian we had before. And let's take the number of terms in the sum to be exactly the same as the number of fields. Then I can actually perform a change of variables, phi equals q theta. That means this q theta becomes just a phi. And all of the interesting activity moves its way over to the kinetic term. And the potential term is completely trivialized. The argument of each cosine is just one of the underlying variables, not some irritating integer linear combination of them. So xi is the new physical metric, and it's gotten by conjugating the original metric by some integer matrix that was somehow given to us. Now, in this presentation of the theory, the fundamental domain is very trivial. It's a hypercube of side length 2 pi. The metric is not completely trivial, but it's constant. So a constant metric in Rn has surfaces of constant distance, which are concentric ellipsoids. That, if you just think of metrics determining ellipses in the plane. The eigensystem of the metric determines a collection of concentric ellipsoids. And so the problem of what is the diameter of this space amounts to the question of what's the largest ellipsoid that I can circumscribe around the fundamental domain without losing contact with it. I mean, if I draw an ellipsoid like this, that's even farther from the origin than these corners of the fundamental domain. That's measuring a larger distance. And something inside is smaller. But then there's one last final one, for example, the picture of the purple one here, that just barely touches 2 corners. It's circumscribed around the fundamental domain. And the distance from the origin to this purple ellipsoid, measured with this metric c, is the diameter of the fundamental domain.
Sounds like the problem with small denominators in social mechanics.
That might be true. I don't know that problem.
You've got a bunch of resonances, that's what the cosine data terms are. And you've got injured relationships.
Yes?
And so that is exactly the problem with small denominators when you try to solve the problem in celestial mechanics.
Oh, great. Okay, so I would be very glad to hear more about this. So in fact, I'm going to come up with a difference. We'll see. It'd be funny if it happened to be the same problem and we have different small denominators, because on the next slide I'll show you what the small denominator is in this problem. Well, it'll be Q transpose Q.
Exactly.
Oh, it is? Oh, no, then it's literally the same problem. Great. So what we're looking for here is small denominators because we want large diameters. Very, very interesting. Okay, great. I had no idea.
Well, the other thing that happens though is when you do this is typically because you've got to couple the solution. You're doing just classical stuff at the moment.
Yeah.
There's no quantum mechanics. You
Yeah.
get chaotic solutions. So these are very interesting dynamics.
Yeah, this is so far totally static and geometric, but I will be very interested to hear how to do this. So what's the small denominator business in this context? So why am I drawing these different ellipses? Okay? It matters to answer the question, if I've got a square, how big is it? Well, in R2 with the trivial metric, if the side length is 2 pi, then the diameter of the square is 2 pi root 2. But we're not using a trivial metric, we're using a constant metric. And the constant metric has some eigensystem that points in some particular pair of directions, indicated by the principal axes of the ellipse. If the principal axes of the ellipse are oriented along the face normals of the square, then the diameter is 2 pi times the Pythagorean sum of the metric eigenvalues. But the best you can possibly do is the purple case. In the purple case, the largest eigenvalue eigenvector of the metric is pointing along a long direction, a long diagonal. In R2, who cares? It's a factor of root 2, but in Rn, it's a factor of root n. And so the longest direction can be 2 pi times the top eigenvalue of the metric, square rooted, times root n. That's the best you could possibly do. Okay, now I don't want to spend a tremendous amount of time on this because I'm not actually going to make my living off of this factor of root n in this talk, although I have done so in previous talks. What I'm going to focus on is the following decomposition of the diameter. So if you actually look into examples, you find that the diameter in real examples very nearly saturates this optimal result. Optimal is, of order Cn root n. And that's what one typically finds, almost the optimal value. But I now write a trivial equation, which you can see if you just cancel these things, where I factor it into 3 pieces. This is notation. For those of you who see the bottom line obscured, k was the metric we started with, without the integer conjugation going into it. It has eigenvalues f1 squared through fn squared. C is the real new physical metric with the integer conjugation. It has eigenvalues c1 squared through cn squared. This is your completely naive estimate of how large the box is. You would say, I don't know, Pythagorean sum of the eigenvalues of the metric. This is the factor of root n I was explaining on the previous slide. So there's an enhancement relative to the dumbest possible estimate. And this is the factor I will be obsessed with for the remainder. This is the real small denominator enhancement, as I'll explain in a minute. Okay. Root n is nice, but the n's I'm thinking about are 10 or 100. These are not gigantic factors. But this could be an exponentially large factor in principle. And so we'd like to know, is there such an exponentially large factor somewhere in the theory space so we can find models with huge diameters? So let's focus now on this effect. So this effect is coming from the orientation of the eigenvectors, namely ellipses versus squares. And this is coming from the lattice of charges, namely what is this matrix Q that we started with? So now the small denominator. Let's find the largest eigenvalue of the metric. Take a trivial case where the original metric is just the identity times a constant. Then the physical metric is 1 over QQ transpose. So if QQ transpose happens to have a smallest eigenvalue, its inverse will have a largest eigenvalue. And so we're just asking the question, if I have some big matrix of integers, and I contract it with its transpose, how small is its smallest eigenvalue? Now, If you let me pick the integers, it can be really small. I can make a super small, smallest eigenvalue, but you have to let me pick. The real question is, what charge matrices should you think of as reasonable or allowable or legitimate in a physical theory? And that is a much harder question to answer. So the two ways you could try and approach this without actually delving into quantum gravity. So in a moment we'll delve into quantum gravity. But if you didn't want to do that, you could sort of sit on the sidelines and say, well, I could imagine that Q is some random matrix and use random matrix theory to study the eigenvalues. And we've done that, and I like the results. There's a strong prediction that you can have a huge diameter. And other people have argued using field theory, ideas in field theory, that some sort of structure in the charge matrix could automatically give you a smallest eigenvalue and so a huge diameter. The question is, can either of these things happen in a quantum gravity theory? And to answer that, you can't anymore sit on the sidelines. We actually just have to jump into the quantum gravity computation. Okay? So for all of the remainder, all we're trying to do is find this object in a legitimate quantum gravity theory, namely in a solution of string theory, and ask, how big is this largest eigenvalue? Is it bigger than m Planck or not bigger than m Planck? And that'll answer everything for us. If the answer is much bigger than m Planck, then we would say, wow, I've found a candidate model somewhere in the NSR plane that could be ruled out by near future experiments. And if I fail to find any examples, I would say, uh-oh, we still do not have anything anywhere within the realm of reach of near experiments. So those are the stakes. So now let's actually just do that. We'll just jump into string theory. So string theory, as you all know, naturally exists in 10 dimensions. And so to connect to 4-dimensional physics, you have to somehow compactify it, which means to consider spacetimes of the form Minkowski space or de Sitter space, what have you, times a compact 6-manifold. In this talk, that compact 6-manifold will be a so-called Calabi-Yau space, but it doesn't matter. So what is the deal with this compactification? From the geometry itself, you can derive directly, like by calculating, the 4-dimensional theory, which is some quantum field theory plus GR. The quantum field theory has some number of scalar fields, including some number of axion fields. It has a metric for the axions. It has a charge matrix for the axions. We just need those data. Now, the geometrization of the problem is quite appealing here, because the possibility of super-Planckian displacements in string theory, which is what we're after, maps into the existence of 6-manifolds with certain topological properties. So now we've turned a cosmological dynamics question into a topology question, and maybe that gets easier when we can solve it. Okay, so now we actually get to the real string theory, or at least stringy geometry computation. The number of axions in the 4-dimensional theory is determined by the number of non-trivial holes in the Calabi-Yau threefold. Depending on which string theory you're talking about, you're interested in different kinds of holes. In our case, which is type 2b on an 0307 orientifold, this number is what's called the Hodge number H11. So there's just some number H11 of x determined by the Calabi-Yau threefold x, which you can in principle calculate and is not super hard to calculate, which tells you the number of axion fields. Okay, fine. So that's just the range over which my indices I and j were running in the previous discussion. But the hard part is to determine the charge matrix, this matrix Q, that determines the metric. And that is determined by counting holomorphic submanifolds D in X that are special. Holomorphic submanifolds that are special in that they admit no deformations. And these things go under the name of rigid divisors. So basically you should think I have some 3-complex dimensional space and I want to count submanifolds in it with special properties and see how many I have. And that answers all of my questions, if I can just do that counting. Now how do you do that? So we want to compute topology of submanifolds in some 6-manifold, a real 6-manifold. And well, you all know that complex analysis is much easier than real analysis, at least if you're going after the same target. Complex analysis is vastly more powerful. Similarly, real analytic geometry, especially in high dimensions, not just like a Riemann surface or something, is way harder than complex geometry. So by going to complex geometry, Calabi-Yau manifolds are complex. Life gets a little easier. But you're still doing complex analysis, which is a pain. Next thing you can do to make your life better is to, instead of doing complex geometry, do complex algebraic geometry. Now you're not solving differential equations, you're solving algebraic equations. You're finding zeros of polynomials. That's much easier. It's still too hard for me. The next step, and this is a really fruitful idea which has been around for decades, is to construct the basic underlying objects of algebraic geometry, which are called varieties, and that just means the solution sets of polynomials, to construct them from combinatorial data. Roughly, if you want to think about the solutions of a bunch of polynomials, you can work with the basis of monomials and try and stitch together your solutions that way. I'm giving a purposely very far away view of this because we're not going to delve into any of these details, but I do think it's important to have a perspective on what we're really trying to do is a computation that would be totally infeasible if we didn't at least have algebraic geometry techniques, and preferably even combinatorial techniques. Once you've reduced it to a combinatorics problem, then you make a computer do the counting, and then you're done. And that's what we've done. So what is this combinatorics? It amounts to finding triangulations of polytopes, and a triangulation of a polytope is just what it sounds like. A polytope is a region in Rn, like that, and a triangulation is just a division of that region into some simplices, like that, subject to various rules. Now you start doing it for a higher and higher dimensional polytope, and you triangulate it in a more and more complicated way, and eventually you hand it over to a computer. But all you're really doing is drawing lines from some origin out to some vertices, and keeping track of how many lines you've drawn and in which places. That's all. So that you can actually do. And when you do it, you can get the data of the metric on the field space and the charge matrix by following some very simple algorithm. You pick a polytope from some database, you triangulate it like this, and then you can read off the intersection numbers, you can count the rigid divisors, and you know the 4D Lagrangian, and you're done. You compute the diameter. That's the program. What's hard about this program is this step, actually, triangulating to reach a toric variety. Also this step, enumerating the rigid divisors. So, I'm not going to show you our precise way of doing the computation, but it might be relevant to just get some perspective on where things stood previously. So finding all the triangulations of some polytope gets sort of costly when H11, the number of fields, is bigger than about 10. So when we first started this undertaking, we knew that there were some nice packages that exist for the purpose of triangulating polytopes. We thought we'll use those, that'll get the job done. And that got us up to about H11 of 10. But we really need to reach into much larger Hodge numbers to solve the general problem. So my student Cody Long thought of a better algorithm. That got us up to 30. But then we've subsequently cracked the problem, and now we can go to H11 of 400. So it used to be that this computation failed at H11 of 10. After hours, it would just crash. And now H11 of 400 is just seconds. So we've just completely got this problem down. The next part is finding these rigid submanifolds, holomorphic submanifolds. Here, too, there was some package that was written by Blumenhagen and company to do this, and that failed at H11 of 5. And we've recently figured out how to get around that, too. Now we can solve that problem also. Now we can get to as large an H11 as you want by hand. So that's good. Now we can do this combinatorics work. We can do the enumeration. That means we can find all these Calabi manifolds. So now here comes the part where we report the results. We studied 4,390 Calabi manifolds, and the largest tensor to scalar ratio we got was smaller than 10 to the minus 3. And there was no good reason that that had to happen, I will say. What I mean by that is that I personally did not know until we opened the box whether we were going to find something at, for example, tensor to scalar ratio of 0.1. I thought we could. Wasn't promising anybody that we would, but I thought it could go that way, could well happen. You know, in some kinds of classes, some ensembles of solutions of string theory, it's obvious that there's a no-go theorem. In this ensemble, it's not obvious. I don't even think there is a no-go theorem. It's just that we struck out after 4,000 tries. So the obvious way to proceed now is to try again and again in other contexts, other corners of this set of solutions, and we will do that. So I should explain what these axes are. This is just a count, it's a histogram, and then R is the field range in units of the Planck mass. So only if this gets out to about 1 are you happy. And the inset shows you this pathetic little tail here, which has one thing out at about a half. So that's as far as we got. Now, you might say, what was all this business about, you know, small denominators and alignment, and the integer charge matrix is giving you this huge effect? Well, I can show you how much of a win we got from that. So here is the effect of alignment. This is counts again, and this is the amount by which alignment improves things. So there's a huge spike at 1 because 2,180 of the cases have no alignment at all. And then the majority of those that remain have anti-alignment. They get worse. And then 494 of them get better. And the best improvement is a factor of 2.5. So that's not going to get it done. Now, I should say, all of this systematic study that we've undertaken, I didn't quite explain that. This is all Calabi-Yau manifolds up to H1104. There's a database. When I said pick a polytope from a database, there's a complete tabulation due to Kreutzer and Skarka, and we just took them all. And this is the answer for that set. But what we have to do is now press on with our new tools to larger H11 and see if the answer that comes out is any different. So just to get a picture of what this thing looks like, so I said this is some polytope. Well, you can define a polytope by its vertices. So this is just the coordinates of the vertices of a polytope. So you can just draw it sometime if you want in R4, and you can picture what this polytope looks like. This is a particular example with 4 fields. And here's its charge matrix. The identity is the trivial case. If the charge matrix is just 1. This is not quite 1. It has the 4th row being a little bit weird. That's it. And what that does is it gives you an alignment by a factor of about 2.5, extending the field range from 0.05 to 0.1. Not much of a win. And then just to show you, here's an example at H11 of 100. The charge matrix is the 97 by 97 identity, and then the last 3 rows have all this crap. And this has a maximum enhancement of a factor of about 8.
So it does increase as you increase the protein.
Well, it depends on which thing. The enhancement does. Eta max increases. However, R decreased. And the reason that R decreased is if you go back to when I had an expression for the field range F over M Planck, that's proportional to 1 over volume to a power, and the power depends on the particular axion in question. As you take a space with, if the space has H11 of 100, that's 100 different 4 cycles in it. And it turns out to be actually true. It's hard to pack a lot of topology into a space without making the space bigger. And so the volume of the space gets big. Here the volume is 10 to the 11, and that shows up in a denominator, and that hurts. And so one of our undertakings right now is to find this sort of Goldilocks cases where the denominator doesn't grow as fast as the numerator grows. And we have not yet zeroed in on those. There's some reason to hope that we could succeed, but this is also a pretty understandable phenomenon, that you're trying to have tons of topology in there, and the topology is not doing as good a job for you as it is costing you. So where do we stand then? You know, the observations overall are in superb agreement with the broad brush predictions of inflation, but what I've been trying to argue throughout this talk is the precise predictions of inflation depend on the nature of quantum gravity. And by the end, we came into contact with a case where that was reduced to a real computation. What is the maximum allowable primordial B-mode signal? And the answer is a factor of at least 100 below the current limit in this sub-ensemble. Now, nobody should take away from this that string theory is supporting some sort of no-go result. I studied an extremely small corner of the solution space of the theory. But it happens to be one of the very few corners where we can answer all the questions. So I'm sort of working my way outward from there, and so far we have not succeeded in giving a gold-plated, nail-it-to-the-wall kind of example where I can say this is a real solution of the theory. Now, I've personally been involved in lots of other projects where we've proposed that we had plausible constructions of large field inflation in string theory, and I'm not taking those back. We do think that those are sort of plausible constructions, but sort of plausible is different from every reasonable observer should agree that these are real. What happened in this work, and the reason that we did this work, is by the end, it's just an answer. It's a collection of integers. You diagonalize this matrix, and you get one number as your answer, and there's no messing around. There's much less theoretical give in answering the question. So what we are left with then is a promising approach to determining when string theory allows Planckian displacements is working in theories of many axions. And now, as I've shown you, we can systematically enumerate such theories. We're just on the cusp of really doing that enumeration. We've only done it in small subsystems using combinatoric methods from toric geometry. We haven't found any super Planckian diameters yet, but stay tuned. And so if you're curious about any of the background stuff that I breezed through early on, I can recommend my book with Daniel Baumann, which you can get for free on the archive. That has a lot of the backstory of what I think is a subject in a very exciting state. Thank you.
So in your 4,000 examples, are there conditions in source?
Yeah, thanks. No, I'm asking a purely kinematic question. So it could be, if I had come forward and said, here's one, I found one, delta phi is 11 m Planck, then the question to ask would have been, oh, does that actually inflate? And the answer would be, no, it doesn't inflate at all. All I'm checking is that the geometric size of the field space, which is a necessary but not sufficient condition, is large enough. And had I done that, I would then have started the heavy lift of controlling the potential and making the whole thing work. So basically, yeah, to elaborate on that a little bit, there's a kinematic condition for large field inflation, which is that the field space is large, and a dynamic condition. The dynamic condition is that the potential is smooth and well behaved. Because the potential is just the sum of cosines, there's not too much difference between those two computations. That's what's nice about axions. But for the purposes of this work, we asked strictly the kinematic question, which is why at the end I was able to reduce it to an entirely geometric computation. There was no, oh, what about quantum corrections to the potential to worry about.
Yeah, I see you chose the type 2B string theory to start with.
Yeah.
What's your motivation for this preference?
Yeah, the motivation actually is that all of this business, okay, so when I showed a picture of the Axion field space, you noted that there were at least as many instanton terms, at least as many hyperplane pairs as the dimension of the space. So this region was compact. If that had failed, that would just mean that there's some linear combination of axions that doesn't appear in the potential. That means you have a flat direction. That axion gets no potential at all. In such a theory, you can't possibly inflate. There would be a runaway instability. And so in type 2B string theory, that's the only theory where we really have a good computational handle at present on finding enough non-perturbative effects. Because after all, each of these is some new string theory instanton effect. And we have to find enough, at least as many independent ones as there are fields. And finding some is trivial in any corner of string theory. Finding as many as there are fields is a hard task. Usually, you make it to the last one, and you can't get that one. Very often in a theory with a string theory construction with n fields, you can find n minus 1 instanton terms, and then the last one slips away from you. It's dual to an understandable statement that there's some reason that some fields should be unstabilized until you've included a sufficiently large collection of effects. So it's a very complicated business. And a shorter answer to your question is, in the current state of development of the subject, type 2B string theory is where we're best at finding vacua and finding effective actions.
But theoretically, all these versions is equivalent to best duality.
Yes, but they're not strong, they're not weak dualities. So when one version is weakly coupled and you can do the computation, the other version is horrendous and inaccessible. And so what would be nice is to find other weakly coupled regions of the duality web where we can do these computations. And we're trying, all of us try in these different corners. It's just that for various reasons, which I'm happy to explain afterward, there are just a few pieces missing in each of the other corners right now. And type 2B, there's been a lot more progress. A deeper answer to why there's been so much more progress in type 2B has to do with mirror symmetry, with the fact that some parts of the type 2B construction are exact at the classical level and receive no corrections. And so you can then get a lot more control over the theory without walking out of bed and running into quantum corrections.
And the Calabi-Yellow is supersymmetry. So where is the Axion part of this Lagrange?
How did a potential arise if it was supersymmetric?
I mean, the superpendler of Axion, is there any difference on?
Yeah, that's actually related to Yisheng's question. So when I said that these things wouldn't inflate and that they have instabilities, what I really mean is that the Saxion field, the superpartner of not the fermion, but the scalar partner of the axion, right? The axion is a single pseudoscalar at the bottom of a chiral multiplet. There's also a real scalar, parity plus. That Saxion field generally parameterizes an instability. It gets a potential. There's a potential rather like this for it, but it's not protected as richly by shift symmetries as axions are, and so it's much harder to tame it. If I succeed, if tomorrow someone emails me and says, hey, we found an example with delta phi of 15 m Planck, the next job, which will take some time, is to tame the potential for the Saxions and establish that inflation can actually occur. We have ideas, but it hasn't been, there's no example where the kinematic preconditions are working well enough that it's worth investing the trouble. But someday we will.
All right, maybe one more question.
Well, the universe is presently inflated. You can't want to constrain theory any further from that simple fact.
Yeah, so, right, let me go back to the two kinds of dependence of inflation on quantum gravity. So this extraordinary, extremely strong dependence really refers to super Planckian displacements. And okay, this is not relevant for this. So the fact, if I strike out forever, even if I could prove to you right now a theorem that says in string theory it is impossible to have delta phi bigger than 10 to the minus 5 m Planck, I will guarantee you there's no such theorem. But even if I could prove that to you, would not say anything forbidding inflation. It would just forbid large field inflation. Now, in fact, I lied a little bit when I asked, are there any things on this graph that are not already excluded? There's this one little one here, low scale spontaneously broken SUSY here, which is at negligibly small r. That one's fine. And the basic point is that the models that are subject to this ordinary dependence, the fact that the models depend on quantum gravity doesn't mean that quantum gravity threatens their existence. It just means that if you want to know the right values of the parameters, you have to do the computation in quantum gravity. So one way of describing that, let me try and give a very short answer to that, would be that if you have, so this could apply for quintessence. You know, if you thought it was not a cosmological constant, but you want to study a quintessence model, you compute, say, the eta parameter. And you can compute that as the value you got being agnostic about quantum gravity plus some correction. And what I'm referring to as the ordinary universal dependence is that this thing is order 1. And so you have to get your head straight about quantum gravity, get your hands dirty, and compute this thing. You find that it's some order 1 number like minus 1.5. And you make this, 1.5 plus 10 to the minus 2, and then you're happy. It's not that big a deal, but you don't know what to fine tune against until you've done this high scale computation. That's all. It's not a threat to existence.
All right, that's probably a good point.